David Gross, welcome. Here we are in your beautiful office in Santa Barbara, overlooking the Pacific Ocean. And I'd like to start with your childhood. A lot of the laureates I speak to took time to find their discipline. They wandered through various subjects. But you seem to know you were a theoretical physicist from your teenage years.
I think I do. I think I did. I think when I was a teenager, I started reading popular science books, and I really got turned on to, what actually happened, to the idea that I wanted to become a theoretical physicist. Although I'm sure I didn't really understand what that meant, but I found it just enormously exciting to read these stories of what were my heroes at the time, like Einstein, who was this unimaginable god-like figure, but Bohr, Heisenberg, who had discovered all of these incredible structures in the physical universe by thinking and by playing with mathematical formulas. And I was always interested in puzzles, and I liked math, but the idea that you could, with your own mind, figure out some deep truth about nature seemed to me awfully exciting, and more exciting than, playing with chemistry sets or building your radio, which I did some of that too. But that's what really grabbed me, and so as far back as I can remember, I felt that that's what I wanted to do. And if you decide to become a theoretical physicist, it's a pretty straight path. I mean, there aren't big obstacles in your way if you're reasonably skilled. But it's more than a theoretical physicist. I really wanted to emulate them, to work in that area of theoretical physics, which is interested in what the fundamental laws are, the big questions, how the universe works at its smallest scale. There are other kinds of theoretical physics, but what attracted me were these great revolutions of the early 20th century, and relativity and atomic theory and quantum mechanics. It just seemed so exciting.
Did you find good books that really pinpointed them?
Not if I compare what was available to me. At the time I was living in Israel, what was available to me was so poor compared to what young people have nowadays. They're just awash in information and resources. There were books by Gamow, Eddington, Einstein, Bridgman, I remember. There were a bunch of... I would go to... there were no libraries in Israel in English, and I would go to the one bookstore that sold English books and always look for the science books. There weren't many, but there were really good ones. There were some.
Because you moved to Israel when you were, 13, 14?
Yeah.
Your family relocated from suburban Washington.
Right.
It must, for a budding theoretical physicist, that must have been a bit of a shock.
I think that interest just began around that time.
Yeah.
One good thing about Israel is there were very few distractions at the time. There was no television.
This is just 7 years after the foundation.
Yeah, right. Yeah. It was a young and rather poor country. We were better off because for a while at least we had sort of diplomatic status as advisors. But there were no distractions, So at the time when I first moved to Jerusalem, there was only one movie theater in town, and there were no television. So I read a lot, and there were disadvantages and advantages. But I was so I was good at math, and that made it easier. And I feel kind of lucky not to have gone through a lot of the what should I do, and there's so many interesting things, what should I choose? I sort of always knew what I wanted to do. But a lot of theoretical physicists of my ilk, once they find their way into that kind of physics, are as equally committed for. It just sometimes takes a bit longer.
Was the school system in Israel developed enough to sort of suit you as you were trying to learn?
It was, in
maths
some
and
ways,
physics?
it was more developed. It was in a different way. I mean, it was a continental style. And when I went to high school, there were in Israel compared to the only a small segment of the population really went to high school. And since there were few opportunities, it was a developing country, rapidly developing, but at the time I went to high school, it wasn't rapidly developed enough so that very well-educated recent graduates of the universities would teach in high school. So in some ways I had better teachers than I would in America, where high school education was much more democratic. But, it was a small country, and there are advantages and disadvantages.
Mm-hmm. Mm-hmm. After reading maths and physics at Hebrew University, you went to Berkeley, and you arrived in the 60s when basically experimental physics was having a golden period. Particle physics results were just pouring out.
Right.
So was that a good time to be a theoretician arriving?
It was, in retrospect, the perfect time. So, I went to Berkeley, which was the center of experimental high-energy physics at the time. By today's standards, a very low-energy machine, but at the time, as you say, discoveries were happening all the time at Berkeley and being discussed at the what used to be called the radiation lab. They've now renamed it to take out the word radiation.
It's a dirty word, I suppose.
Yes,
Yeah.
so now it's the Lawrence Berkeley lab, but it used to be the Lawrence Radiation Lab. So it was very exciting, and in theoretical physics, which was what I was interested in, it was also very exciting. Although certainly in retrospect, the theorists were doing pretty badly, and the experimentalists were doing very well and discovering all sorts of wonderful things. It was a great time. Berkeley was also a fascinating place to be in the early 60s. So.
There must have been a sense of urgency amongst the theoreticians that we've got to solve all these puzzles that are being produced.
There was a sense. I mean, theorists always have their ideas, so there was a sense of, I wouldn't say urgency, there wasn't a sense of great accomplishment. There was a sense sometimes of, these problems are impossible and they'll take forever, or everything we've tried doesn't work, so we need some totally revolutionary ideas. It's more the latter that I got caught up into with my advisor, and it was sort of the predominant feeling. The theorists at the time were trying to figure out what clues they could get from these experiments. In the field I went into, which was trying to understand what used to be called the strong interactions, the nuclear force, that was especially hard.
So this is the force that holds quarks together.
Right. At the time, in retrospect, we now understand that what was understood and what was tried was all wrong directions and misleading, and very few things survived from that early 60s. And the general direction of most of the field was really wrong. But one didn't have a sense of that, you don't realize that.
Although you did your thesis on the previous theory.
I did my thesis, well, it wasn't a theory, it was an approach which didn't take me that long to get disillusioned with, but it really was an approach which said, since there's no traditional theory, I mean, in theoretical physics one is used to have a theory. You write down equations, and if you could solve these equations, you could figure out how the force works and what is the mass of the proton and so on. Well, all the attempts at that time, the last decade or longer, 2 decades, had just been miserable failures. And so there was a very strong feeling among a lot of people, led among the rest by my advisor, that that since it was so hard to construct a theory, maybe there's no theory at all, at least in the usual sense. One really needs a revolutionary approach and it was called the bootstrap, which means you never wrote down equations, which if you could solve, you could explain everything. No, there were no equations. There was no systematic way. In fact, you just sort of bootstrapped the answer into being. And by assuming there has to be some input, the input was very general principles like causality. A precedes B. Your grandfather produced you and not vice versa. That was marginally successful because, everything is connected somehow, so people would assume a lot and then deduce a little, or assume a little and deduce a little more, but it wasn't very satisfactory. And it was an interesting period, very different than today, where theory has been pretty successful in particle physics for the last 30 years. And the experimenters haven't been finding really new things, by and large. At the time I started, it was the reverse. So in retrospect, it was a good time to be a theorist. At the time, one felt, especially the older people, that very frustrated and resorted to these rather extreme points of view.
Mm-hmm. So you branched off on your own, and you moved to Harvard and then Princeton.
Right.
And in the interview we recorded with you in 2004, you talked, which was recorded with Frank Wilczek.
Right.
You talked about the development of quantum chromodynamics.
Right.
But I just wanted to concentrate on one aspect of that, which was your relationship with Wilczek. He was one of your first graduate students.
He was actually my first.
That's right.
He began to work with me, in 71. Right.
It's a good start. It's how did the relationship work?
Well, I guess I hadn't had. I think I might have had another student wanted to work with me and eventually did, but Frank was ready and started work. So I hadn't had any graduate students working with me directly beforehand, just colleagues, and I didn't really. So Frank sort of spoiled me to some extent, and I've had some great students, but it was my first student, and he was smart enough to work with me as a colleague. Besides, that's how I like to work anyway. So we just started working as if he was another, and he was up to it. Since I've learned that not all students are up to his level, Frank got his education. He started as a math student at the University of Chicago, and at Princeton he was started as a student in the math department. I was teaching quantum field theory at the time. He took my course and then did well enough so that we transferred him, and he started working with me. So and probably I learned to mentor by mentoring him, and he learned to be mentored. So it was actually a learning experience for me because I hadn't had somebody working directly before then. I was just a new assistant professor.
Set the bar quite high for graduate students to follow. But
well, I've had some good ones. Ed Witten came a year later, and he was pretty good. So there have been a whole bunch of very good students. Princeton had a lot of students. I was lucky because Kurt Callan, my colleague at Princeton, and I were sort of new newly appointed, and there was a kind of a gap between us and the next generation. So a lot of the smarter young people who realized that, well, maybe take a chance instead of going with one of the old masters, with one of these young, more enthusiastic people who have more time. So we got a lot of good students, and Princeton was always a source of great students.
How did you pick them? What did you look for?
Well, the ability to do physics, be creative, independent. And actually with me it was, the way I would judge that is if they could work with me. And by working with me, I really treated my students like, like I would treat any other colleague. So they weren't students, they were supposed to, and not all of them, I learned later, could handle this. But that was, if we couldn't work together, so, I wouldn't give them problems and go off, I never. So if they couldn't work with me, then they couldn't work with me.
So the problem.
It's very easy.
The problem was formulated, they were working on the solution.
They were working on a problem that I was working on as a colleague. Now that isn't always easy to do that from day one. You're part of the mentoring process of a graduate in theoretical physics. Experimental physics, you go build this instrument, come back in a year, or I'll look over your shoulder every week. Very different. And some theorists also deal with graduate students that way. Here's a little problem that I have, and go work on it. But I, by and large, didn't do that, as I really worked with them. And so they learned that way, but they also had to be, it wasn't, especially when I was younger and less tolerant, didn't work very well if they couldn't actually work with me, and needed too much guidance, or if they weren't colleagues. So that actually is the best. When you get letters of recommendation for great graduate students, they always say, this student is so great, he's more like a colleague than a student. And that's sort of the way, what I tried to, in the beginning, to demand, and later, as I had more students, to expect, to train them to be. Because in the end, students have to turn it rapidly into colleagues, into functioning physicists.
Mm. I want to turn to the adoption of problems. You worked on quantum chromodynamics for about a decade after the 73 paper.
Yeah, this was exciting. We had a theory. Could actually write down the equations, which, if you could solve, you could predict the mass of the proton and all these things. And not only was it a theory in that sense, it was a very beautiful and simple theory, simple to write down, with almost no parameters. And so, we wanted to calculate whatever we can using the theory, and because of this feature of asymptotic freedom, there were lots of calculations you could do. That was good, but we also wanted to solve the theory, so-called solve the theory. Find, and especially in the domain where it wasn't easy to calculate, but conceptually difficult.
So by solve the theory, the theory described the behavior, but by solve the theory you mean
The theory described the behavior in one domain, which was how we got to it. When theory is a theory of colored objects, quarks, and gluons that transmit the force, which themselves are colored and sources of this force. And at very high energies, or when all the particles are close together, the forces are weak. That's the phenomena of asymptotic freedom.
That's the paradoxical phenomenon.
Well, not once you can understand it. It was paradoxical, but there, and that's why we were led to QCD. But that's a property of quarks at very short distances. You could test that in experiments that are performed at very high energies that probe very short distances. That was the clue that led us to that. But it could be then, the theory itself could be quantitatively tested, and you could make predictions, which ultimately took years, were verified. Lots and lots of predictions. That goes on even today. But when you pull the quarks apart, the flip side of that, which was equally compelling, was that this force got stronger, and that's why you could never pull the quarks out. That's called sometimes infrared slavery as opposed to asymptotic freedom. Large distances, infrared, the force gets are strong. We thought that was the reason that quarks were confined inside nuclei. But that was just a pretty wild idea, actually. And we didn't even have a good qualitative picture of how that could happen or any analogs. It seemed totally crazy, and a lot of people were very skeptical. And besides, the observable properties of nucleons, of the nucleus, and so on, are all bound up in this strong force at large distances. But in principle, if the theory was right, you should be able to solve it even when it isn't weakly interacting and easy. You might need some new ideas. So I spent a lot of time on this ambitious goal of trying to solve the theory and prove that the quarks were really confined and calculate the mass of the proton. And, like often happens, one is overconfident. I really was sure it would take about 5, 6, 7 years, a decade. So the theory is still not solved in that sense. We now can calculate the mass of the proton and the mass of all these particles that are made up out of quarks. But we've had to resort to putting the equations on a massive parallel computers and having hundreds of people work for years to do these calculations. And it works, agrees with measurements. It's still not satisfactory. It's not something you can do on the back of an envelope. We've learned a lot qualitatively about the nuclear force in these years. A lot of beautiful work has been done. So the qualitative picture is in shape, and now actually we're getting to the position where some close cousins of QCD, which have more symmetries and in some limit, which is not quite under control, can be solved. And it actually relates to string theory, although a lot of input from string theory. So eventually we will solve this theory, but it's taken not 10 years, but it's been now 35 years, and it'll probably take another 35, 50 years. But this theory is going to be around forever, so
yeah, there's time.
There's time.
But the question is, how do you know? How do you know? How do you feel? When is the time?
I made a mistake. You see, I was. So we actually, in developing, trying to find different ways of solving this theory, over the years, over the last 35 years, people, physicists, many physicists were involved, thinking about this and still are, have invented, I don't know, maybe a dozen very deep tools and qualitative understanding, which connects to all sorts of other areas of elementary particle physics and condensed matter physics, for that matter. So the goal is often very important, even if it's not realized. Having a goal set by nature, what is the structure of the nucleon at large distances? Assuming the theory is you're on the right track. Having such ambitious goals can be enormously productive, even if it takes 50 years to solve the problem. But there's an example where I must say, so the goal, me and the rest of the community came up with a lot of important ideas along the way. But the goal is still out there, at least the original goal. Whereas in the case of the previous success of trying to find an explanation for scaling for this point-like behavior of quarks inside the nucleon at short distances, there I was also wrong in the sense that I and the whole community thought that understanding that was essentially impossible, a distant goal, and constructing a theory of the strong force would take decades. It was sort of unimaginable that one could do that. And then it all fell into our laps within a year or two. So choosing the right problem is a complicated thing. It's more what's really important is choosing the right direction. If you're going, there's a mountain peak out there you want to climb, you don't always know how difficult it's going to be, even if you can see it. And you might have to pass over a few intermediate peaks on the way. But if you're going in the wrong direction, you're lost. You'll never get there. You're in the right direction. It might be easy, it might be hard. That's important. So choosing the right question is really direction, a set of tools. And very clever people go off in very apparently interesting other directions which lead nowhere.
Yeah, and the history of science belongs to the people who've chosen the right direction.
Right, and so that's also complex because what's important is to be, and not totally easy for anyone, to be open to input from nature, to recognize the clues that nature, which are the only really solid clues you get, to ignore the misleading clues from experimenters or observers who make mistakes. So it's always a noisy environment with the signal and noise often equally loud, and to be open to other explorers, who can give you information too. So, too often, people who haven't gone the right direction are often because they're too obsessed with their own ideas and not open to clues from nature or from their colleagues. And then there's this ill-defined intuition, which it's impossible to describe, this gut feeling you have that you can't quantify, but you have to trust. You have to have it, and I don't know what it is, and you have to trust it, even though it's not what most people are doing.
Was it gut feeling that moved you in '84 or so from QCD to string theory?
Yeah, to some extent. Although I had been interested in string theory at its birth for about a year or two, which is 40 years ago, in '68. So I played around with it from '69 to '70, '68 to '70. Right. Partly that this was the right direction, sense of direction, that this approach had so many compelling features that, and at that time there were some big advances that we made that were happening that convinced a lot of us that once again that we'll solve this theory in a decade. But as it turned out, again, these things. There's something about I often say that you have to be an optimist, and I certainly have been in my life about this kind of theoretical physics because it's so hard, and the problems are often much harder than you think. And if you're not an optimist, you'd give up. So the pessimists don't survive long in the field, and you're just left with the optimists. But there were a lot of clues, which is why. So when this so-called string evolution began, a lot of clues open. There were a lot of signs that string theory had a lot going for it, and that hasn't really changed. The only thing that's changed is that it appears richer and the problems are more severe than we thought, but those features are still compelling. Which is why even after, that was 24 years ago, people continue, and still some of the best, or if not the best, young theoretical physicists who are interested in this direction of fundamental physics still end up being string theorists.
I'm sure it's too simplistic to make this comparison, but when you arrived in Berkeley, you were deluged with experimental data and waiting for theory.
Yes.
Is it now the case a bit that string theory is waiting for experimental data from extremely expensive experiments that are hard to...
Well, we all are, not just string theorists. Anyone interested in this, particle theorist. I regard myself as a particle theorist, a string. All these labels are a bit meaningless. Anyone who's interested in the basic what are the basic constituents of matter? What are the forces acting on them? How can we unify the forces? All of those questions, we have been waiting for clues from nature for a long time. And that's a very unusual situation which we face in fundamental physics. It's a fact of nature that what we clearly can identify as a fundamental scale, perhaps the fundamental scale of physics, corresponds to extraordinarily short distances and high energies, which is the same, beyond anything we could hope to directly observe. And but there are a lot of aspects of some of our speculations that might be just around the corner. And so we're waiting for those with anticipation. And these big machines you talk about, the one that has been under construction now for 15 years.
The Large Hadron Collider. Yeah.
Is the LHC at CERN, which is going to produce its first collisions of protons next week, in 10 days from now. And the whole community, the thousands of experimenters who are been working on the detectors and the experiments for years, and the particle physicists and the string, everyone is waiting with bated breath. I just came back from the annual Strings Conference at CERN, at the LHC site. And so this community, which is really speculating about constructing an explanation of how the forces unify and how we might observe some of the new predictions at the LHC, even though most of the time they work at this much higher scale where they understand what's going on and then try to extrapolate that to this much, much larger scale. They too are waiting with bated breath. Not that they're going to prove string theory is right at the LHC. That's extremely unlikely. But what we do expect is there will be really fundamental discoveries and ones that will give us some clues. We need clues. The problem is harder than we thought.
Does it worry you that experimental physics has become such a big operation?
Very much, very much. It's I had 4 years ago, just at the time of the prize actually, we had a conference here celebrating our 25th anniversary, in which I ended by posing 25 questions for the next 25 years in physics. The last question was actually suggested by an astrophysicist And it was, what are we going to do about the impending crisis in fundamental physics and particle physics and in cosmology as well? Because in both cases, the instruments we need, it looks like within the next 25 years, we're going to get to a point where it'll take too long, it'll be too expensive and too big, too many people to go the next stage. And not just in particle physics, where the problem might be right with us already, but in astrophysics, cosmology, the observatories we put out into space, the instruments that people dream of nowadays are also approaching the multi-billion-dollar, 15-year, hundreds and hundreds of people having to work on them scale. And we might get to a point where we simply say, okay, can't do it. And in particle physics, we might already be very close to that point as we dream beyond the LHC. And these big questions, like how do we unify forces of nature, how did the universe begin, these enormous, deep scientific questions are still going to be out there. And it is scary to imagine that humankind will get to the point where we still have these deep questions and simply can't afford or don't have the will, or it becomes humanly impossible to answer them experimentally, observationally. So what do we do? I don't have an answer, but I think we need to think about it as it becomes more real. People are worried about that. It would sort of be depressing. It would be almost as depressing as a question I often get asked, are we smart enough to understand understand string theory, understand the basic laws of physics? Maybe we're just, too dumb.
It'd be depressing if that were true, yes.
Yeah, but it would be all equally depressing if we just couldn't afford or didn't have the will to do projects like the LHC or beyond. The LHC is, I think it's the most complex scientific project ever carried out. But it's hard to imagine doing something 10 times larger.
You say you don't have an answer, but do you have an inkling of an answer?
No, not really. It's a problem for society, too. Societies, depends how much we value knowledge and whether we're willing to give up at some point, which, I don't know. We'll see. Yes. Maybe we need I don't know. But we have to be aware of the danger, and it would be pretty depressing if we had to admit that, there are questions we're just not going to be able to approach because experimentally, and because it's just beyond us. We're limited as humans. I mean, for the last few thousand years, we haven't had that feeling. We can do anything. It's a very common feeling in the United States, right? We can do anything. Just give us.
Yeah, countries founded on it. That's right. Yeah. Okay. Well, on the subject of questions, you moved in '96 to the Institute of Theoretical Physics here in Santa Barbara, which is a place that is devoted to interdisciplinary interchange between different areas of physics. What promoted that move? You'd been offered the job before and you hadn't taken it.
Right. Well, I was too young then, and too much engaged in. But partly just a change from being a professor and teaching, year after year. Science changes, but the institutional challenges remain the same. It's also rather beautiful out here. Many reasons, but this is a very exciting place. And it does indeed bring together people who do physics here and from many different areas of science. Anything that's done here we call physics, but it includes biology and climate science and everything, a lot of things that physicists do. So I've enjoyed it enormously. In some sense, it's, my job is to learn about all these areas so I can help structure these programs. And so when I'm here, I make a point to have fun by going to lectures and participating in all these programs. So it's, to some extent, part of my job is going back to school, and when you're, so that sort of, I no longer, as director, teach, except dealing with graduate students, and that, instead I'm a student again, so that's great. And I've learned a lot about areas of physics, which, because one tends to get rather specialized, one gets out of touch with, and a lot of biology, which I never knew much about, and a lot of astrophysics, condensed matter physics, even a lot about the climate last spring. So it's wonderful, and I really enjoy that. It's the funnest part of the job. And but in addition to being, having this interdisciplinary nature and trying to bring these different fields often together on a scientific problem, we also do core science and a lot of string theory programs and a lot of particle physics programs. So it's a very exciting place to be.
Mm. Are you trying to predict who should be talking to who, partly?
Well, we try to choose good programs, good topics, timely topics, get the right people to organize it and attract the best people who attract the best people, get them in place, and then often have different programs overlap. That's not easy to do, but when it happens, it's very powerful. Or we try to help in the creation of new fields which are at the borderline between established fields, something very difficult to do in universities with their departments, but easy here, and we've gotten pretty good at it. Physics and biology, or atomic physics and condensed matter. So new fields need help in coalescing and getting together and creating a new direction.
You've been here 12 years. What are you hoping to do next year?
Well, better. More or less the same, but a lot better. And it's always different. Every year is different, and so it's never the same, even though the structure is the same. So, there's always interesting, we run now, we've grown since I've been here in our scope and our, and how much we do to get, so I always have, a dozen or so programs, 2 to 3 months each year to look forward to, and among those there are usually quite a few that I'm really interested in.
Okay, well, thank you very much. I suppose I should ask where you're going to be in 10 days' time when they turn the LHC on. Are you going to...
I'm 10 days' time. I'm going to be in Norway.
I guess nothing's going to happen that day, but it's going to be a big day nonetheless.
No. Well, actually, they might very well have the first collisions on September 8th or not, 10th is a goal. Might be the 11th or 12th. There's no discrete time. The machines like this, they turn on very slowly. At full strength, the beam itself, the circulating protons, have a total energy in the beams that's comparable to the kinetic energy of an aircraft carrier moving at 32 knots. So you have to be very careful when you start this up, because if they lose the beam and it hits the walls of the container, which have 50,000 tons of magnets, which are cooled to 1.9 degrees Kelvin. It could be quite a serious problem. So they begin slowly, and around September 10th is when they'll have the first collisions, and they'll collide them and then stop and check it out. It'll be something about a year before they're ready to really get the exciting physics.
Yeah, because actually it's quite there's a sort of science and media interaction problem here, that there has been such a build-up to the turn-on that everybody's going to be reporting what happens on September 10th or whatever, and nothing's going to happen, as you say.
September 10th, yeah, there is a whole, right, they're ready for that. Luckily, the media can't get down into the tunnel and make a real mess of things, but they can, so they've already had some champagne. They got a lot of champagne stored away, I gather, because there are a whole sequence of thresholds. They already passed the first one, and in fact, I think it was sometime last week when they had the first protons going part of the way in one direction. That was their first toasts. And then later in that week, this was the week I was there, they had protons going the other way. They had a second. Yeah. Most of the accelerators in France, so they like to drink wine and champagne. September 10th, first collisions, they'll probably open a few more bottles, but then there are a whole sequence of milestones and occasions. There's official inauguration on October 21st. That's when Sarkozy and others arrive. There'll be quite an event there. I might go to that one. Looks like fun. But I don't think the event we're all really waiting for is the first event that is surprising, is an indication of something new, a new particle, what the discoveries I'm waiting for them to discover.
And the first notice of that will be on the preprint servers, or will it be prior to that? Will it come? There'll be something on the grapevine first.
Who knows? There's so many people watching this experiment. There's so many people involved. And as you say, as we talked about, the last 30 years, there's been so little surprises, so few surprises, that who knows how it'll leak out. But inevitably it'll leak out long before it's pre-printed on the archive. So it looks very exciting, and we're all very excited. Hopefully they will make great discoveries.
You presumably do have over the years developed ways that you deal with students, not only what you look for them in them, but the sort of thing.
We covered it in bit. I mean, I've had a lot of very good students, but whether that's because I made them very good or they were very good to begin with, I don't know. They certainly have to be very good to begin with.
But you certainly don't seem to distinguish between students and postdocs, really, or they're just collaborators.
That's my goal.
Yeah.
It works with the really good students, and I've had quite a few of those.
Do you still have students here?
At the moment, my last student just graduated last year, and I've been reluctant to take anyone because my schedule is so crazy that it's hard to really give them the attention they need. But I probably will, because I can't, I enjoy that too much. But there's no recipe. It's just it's chemistry. There's no theoretical physics is very different than experimental physics, where you go to a laboratory. There's stuff to be done. The thing that I treasure, people, theoretical physics treasure, are Same with postdocs. We don't hire postdocs and tell them what to do in theoretical particle physics. There are no projects, by and large. We hire the best students, and they're given total independence. It's very different than experimental areas or big labs where you have the professor who heads a big lab and hires postdocs, and they carry out his ideas, her ideas. That's not how we work. So the students, by and large, the postdocs, by and large, are treated as independent researchers. And students are in that position as well. So I never really regarded it. With the really good students, there was little distinction. And it was very, as they pass smoothly from one to the other going on in life. And what is really treasured is students who can have their own ideas. That's the real rarity. I mean, asking the right questions, coming up with the right problem, as you were sort of getting into, but didn't totally, is the hardest thing. And that's what's really, I look for and try to. But it's hard to do. And I find that, I think the best way, which is possible in theoretical physics, is to work together on a project, because then they can really learn how other, people, how it works.
So I suppose it's easy to ask questions, but asking the right question is
asking questions that are answerable, that lead somewhere, but also questions that are. The two dangers are asking questions that can't be really answered or too difficult, or asking questions that are too trivial and uninteresting. Finding the mean, the golden mean of questions that are non-trivial and non-impossible is, asking those kind of questions is more than half the work. So it's more important to teach students how to do that than to actually have them solve a particular question that you give them and they go away. That's good too. But
yeah, they need something under their belt, but they need the skill, the tool.
They need something that is impossible to teach directly, except by imitating in a way, or they just have it naturally, which is unusual. Part of the problem is that the educational experience we put kids through acts against that in many ways, and it teaches people to take exams and learn what the right answers are, not to ask questions. And then they get to the stage where, and I've seen this over and over again with really brilliant students who are at the top of their classes, and and they just turn out to be crummy physicists because they're not taught to ask questions, or they're taught to answer questions, old questions which we know their answers. We made them up so there would be an answer in 1 hour and 30 minutes. Bad can be very bad education. How do you teach people to ask questions? So.
It was always the complaint about doctors, that they start out as the most brilliant students in
Right.
biology or whatever, and then they just taught they need to find the answers.
And they are put through the sieve of these examinations to choose a small, so they learn how to, answer these well-defined questions that choose them. But that's not what makes a creative scientist, or anyone creative in any field. So I don't know. In Princeton, where I did most of my career was, one was very lucky because the students were very good to begin with, attracted some of the best, if not the best. And then we had a system which has slightly gone downhill since I left, I must say, where there were no required courses. The students who came in were treated like grown-ups. One exam, qualifying exam, and you should prepare for it, and a whole bunch of courses. But you could just take the exam if you're ready. So that, it's in your hands. You're an adult. And it worked for the really brilliant students. It worked very well.
On that positive note, thank you very much indeed.
Pleasure.